we have seen in the previous videos, a PN junction is the basic building block of many semiconductor devices like diodes, transistors, etc. A semiconductor diode is basically a PN junction with metallic contacts provided at the ends for the application of an external voltage. It's a two-terminal device, and in this video, we discuss some of the junction diodes developed for different applications. Let us begin with zener diode. It's named after its inventor zener. It's a special purpose semiconductor diode that is designed to operate under reverse bias in the breakdown region. A zener diode operates just like a normal diode when it is forward biased. It can operate continuously without being damaged in the region of reverse breakdown voltage. The symbol for zener diode is shown here. Zener diode is fabricated by heavily doping the P and N sides of a junction. As a result of this, the depletion region formed is very thin, of the order of 10 to the power minus 6 meter, and the electric field of the junction is extremely high, that is nearly 5 times 10 to the power 6 volt per meter, even for a small reverse bias voltage of about 5 volts. The IV characteristics of a zener diode is shown here. From the graph, we can see that when the applied reverse bias voltage reaches the breakdown voltage, that is denoted by V sub Z of the zener diode, there is a large change in the current. Or at first, when receiving the reverse voltage, the current is very small, and this is called the leakage current that is flowing through the diode. Once it hits the zener breakdown voltage, the current drastically increases, and this current is called the avalanche current because it spikes so drastically. This breakdown voltage V sub Z is of high significance as a large change in the current can be produced by almost insignificant change in the reverse bias voltage. In other words, we can say that zener voltage remains constant even though current through the zener diode varies over a wide range. This makes the zener diode useful in applications such as voltage regulation. Let us try to figure out how or why this reverse current suddenly increases at the breakdown voltage. As we know, the reverse current is due to the flow of electrons from the P side to the N side and the flow of holes from the N side to the P side. That is due to the flow of minority charge carriers. As the reverse bias voltage is increased, the electric field at the junction becomes significant, and when this reverse bias voltage is equal to the breakdown voltage, then the electric field strength is high enough to pull the valence electrons from the host atoms on the P side that are accelerated to the N side. These electrons account for high current observed at the breakdown. The emission of electrons from the host atoms due to the high electric field is called internal field emission or field ionization. This most important characteristic of a zener diode, as stated before, allows it to act as a voltage regulator in a circuit. The voltage that is dropped across a zener will not exceed its breakdown or zener voltage even if the voltage or current in the circuit increases, which is what depicted in the IV characteristics curve. As the AC input voltage of a rectifier fluctuates, its rectified output also fluctuates. In order to get a constant DC voltage from the DC unregulated output of a rectifier, we use a zener diode. The circuit diagram is shown here. Here, the unregulated DC voltage is connected to the reverse biased zener diode through a series resistor RS. The increase of the input voltage will cause the current to increase through RS and zener diode. As a result, the voltage drop across RS increases without any change in the voltage across the zener diode. This is because in the breakdown region, the zener voltage remains constant even though the current through the zener diode changes. Similarly, the decrease in the input voltage will cause the current to decrease through RS and zener diode. The voltage drop across RS decreases. However, there is no change in the voltage across the zener diode. Therefore, any increase or decrease in the input voltage will result in an increase or decrease of the voltage drop across RS, and that too without any change in the voltage drop across the zener diode. Therefore, the zener diode acts as a voltage regulator. Also, we must make sure that the zener diode is selected according to the required output voltage and according to the series resistance Rs. Moving on to the optoelectronic junction devices, here we deal with the semiconductor diodes in which the carriers are generated by photons or by photoexcitation. All these devices are called optoelectronic devices. We study about the following optoelectronic devices. The first one is photodiode, that is used for detecting optical signals. Then we have the light emitting diodes or LEDs that can convert electrical energy into light, and photovoltaic devices that convert optical radiation into electricity, for example solar cells. Let us discuss about photodiodes. Photodiodes are light sensitive semiconductor diodes. It's a special purpose PN junction diode that is fabricated to operate under reverse bias. When the device is illuminated with light of energy greater than the energy gap of the semiconductor, then the electron-hole pairs are generated. The diode is designed in such a way that the generation of electron-hole pairs take place in or around the depletion region. As a result of electric field of the junction, the electrons and holes are separated and the electrons reach the N side and holes reach the P side. This gives rise to an EMF, and when connected to an external load, the current flows. Also, the magnitude of the photocurrent depends on the intensity of the incident light. We can easily observe the change in the current with a change in the light intensity if a reverse bias is applied. Thus, a photodiode can be used as a photodetector to detect optical signals. The IV characteristics of a photodiode is shown here, and we can conclude that the photocurrent is proportional to the incident light intensity. Moving on to light emitting diode or LED, which is a heavily doped PN junction that is made to work under forward bias, and it emits spontaneous radiation. When the diode is forward biased, electrons are sent from N to P region and holes are sent from P to N region. At the junction boundary, the concentration of minority carriers increases compared to the equilibrium concentration or when there is no bias. At the junction boundary, the excess minority carriers recombine with majority carriers near the junction. On recombination, the energy is released in the form of photons, and photons with energy equal to or slightly less than the band gap are emitted. The symbol for an LED is shown here. The intensity of light emitted is less when the forward current is less. As the forward current increases, intensity of light increases and it reaches a maximum value. Further increase in the forward current results in decrease of light intensity, and the LEDs are biased such that the light emitting efficiency is maximum. The VI characteristics of an LED is similar to that of a silicon junction diode, with a threshold voltage much higher and slightly different for each color. The reverse breakdown voltage of LEDs are very low. Also, LEDs that emit red, yellow, orange, green and blue light are commercially available. The required band gap for the semiconductor used for fabrication of visible LEDs must at least be 1.8 electron volt. The compound semiconductor gallium arsenide phosphide is used for making LEDs of different color. LEDs are widely used standard source of light in electrical equipment. It finds applications in optical communication, element security systems, remote control operations, robotics, etc. We can now list the advantages of LED over conventional incandescent low power lamps. This includes the low operational voltage and less power, the fast action and no warm-up time. The band gap of the emitted light is 100 angstrom to 500 angstrom, or we can say that it is nearly monochromatic. Also, LEDs have long life and ruggedness and also fast on-off switching capability. A solar cell is a PN junction which generates EMF when solar radiation falls on the PN junction. It converts the energy of light directly into electricity by the photovoltaic effect. A simple PN junction solar cell includes a P-silicon wafer of about 300 micrometer, over which a thin layer of N-silicon is grown on one side by the diffusion process. On the other side of the P-silicon, it will be coated with a metal, and this will act as a back contact. On top of the N-silicon layer, the metal finger electrode is deposited, which acts as a front contact. The generation of EMF by a solar cell as light falls on it is basically due to the following three basic processes, that is the generation, separation and collection. So step 1 is the generation of electron-hole pairs due to the light with energy greater than the band gap or close to the junction. Then there is a separation of electrons and holes due to the electric field of the depletion region. The electrons will be moved to the N side and holes to the P side. And following this, or the third step, will be the electrons reaching the N side are collected by the front contact and the holes reaching the P side are collected by the back contact. This P side becomes positive and N side becomes negative, giving rise to photovoltage. When an external load is connected, the photocurrent will flow as shown in the figure. Also, a typical IV characteristic of a solar cell is shown here. A solar cell does not draw current but supplies the same to the load. Semiconductors with band gap close to 1.5 electron volt are ideal materials for solar cell fabrication. Some examples are semiconductors like silicon, gallium arsenide, cadmium telluride, etc. The most important criteria for the selection of a material for solar cell fabrication are the band gap, high optical absorption, electrical conductivity, availability of the raw materials, and the cost. Any light with photon energies greater than the band gap can be used for solar cell, and sunlight is not always necessary. Solar cells have applications in transportation as solar energy is used in cars, solar powered calculators use photovoltaic cells, and another is the solar cell panels. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.